Hello. So lesson 15, halfway. Now, on Thursday this week, we will have midterm exam. And that's in usual class time. But speaking to some students, for them, usual class time is the middle of the night. So I want to say, for students in locations where exam time is local time between 11 at night and 7 in the morning, or you have another class at the same time, I know some students are in that situation. Then complete the exam as soon as possible. After 0700 or after class. So one, message TA to let them know you will do this. And two, send completed exam directly to TA, in whichever way you usually send it. Okay, any questions about that or about the midterm in general? Ah, yes. So for some, the calculus midterm is at 6 in the morning. I guess with these new rules, it's going to be at 7 in the morning. Now, okay. So if there's no questions on that. Yeah, so once again, the subject of the midterm exam is lessons 1 to 11, so not today's lesson. Okay. So some review. Review the function sine x over x. So two useful facts about this function. The limit as x goes to 0 and the limit as x goes to infinity. So let's start with the limit as x goes to 0. So recall the limit is 1. So we proved this before, but let me give a rough argument to make it maybe more clear. So imagine a triangle where the angle is very small. So like this, yeah. And say this is right angle triangle. And say the longest edge is length 1. And this angle here, let's say that's x. Then sine is the opposite edge over the longest edge. So this edge, I'm going to write it here, has length sine x. And now, if we imagine now that the left-hand point is the center of a circle of radius 1, and I take this little bit of the circle, this is an arc of a circle, and the length of that arc is x. If we measure x in radian units. That's why these radian units are so convenient. And so, from picture, for small x, sine x and x are approximately the same, because you can see the arc and the vertical edge are very close. So that's not a proof. We gave a proof earlier, but maybe it helps to remember this fact that the limit of sine x over x is 1. So now let's draw the graph of this function. So if this is the x-axis, then it's like this. Quite. Okay. Not the easiest graph to draw, but that's not bad. Oh, but this is not straight, so try and make it straight, like that. No, not good enough. So yeah, I think this is going to be good enough to show you what happens. Yes. Let's make it a bit bigger. So we have the x-axis, and this starts off looking like the graphs of sine x. In the middle, it looks like the graph of sine x. So here I'm drawing sine x over x. So that function is not defined at x equals 0 because we divide by x. But the limit is 1. So for small values of x, the function is approximately 1. And then when I come to pi, sine x is 0, and 2 pi, and 3 pi. But as I increase x, I'm dividing by a bigger and bigger denominator. So the waves of sine x get smaller. So minus pi here. Minus 3 pi. Okay. And as usual, I haven't done this perfectly. Pi and 2 pi and 3 pi should be evenly spaced. But you get the idea. And also now the limit as x goes to infinity of sine x over x is 0. So this means that when x is big and positive, you can make sine x over x as small as you like by making x very big. So we gave a formal definition of this, but that's the idea. And how can we prove this? We can prove it by sandwich theorem. So sine x has a range between -1 and 1. And so sine x over x is sandwiched by -1 over x and 1 over x. And now we can use that the limit as x goes to infinity of 1 over x is 0. And the same for -1 over x. Okay. So this claim about the limit is something we prove directly. And then using the limit laws, if I know the limit of a function, then I know the limit of a constant function minus 1 times that function. And that's also going to be 0. Okay. So we were talking about extrema. And that means maximums and minimums. So let's give an example, just to remind us. So maybe this. So here we have a local maximum. Because there is an interval near this point such that that point is the largest value. And in the same way, this is a local minimum. But here, at least from the function, the part of the function I've drawn, let's assume this is the whole domain, we have a global maximum. Yeah, so let's assume we have the whole domain here. The global maximum at the top and a global minimum because the value at that point, the values elsewhere are always higher. So we said that extrema occur at critical points and endpoints. Critical points where the function's derivative is 0 or it's not defined. And we can use the derivative to say what sort of extrema we have. So the first derivative test is what does this for us. So some examples. Let's give some examples of f of x and f prime. So our usual x squared and so the derivative of that is 2x. Sketch a graph. Like this. And that has a minimum at x equals 0. But change the coefficients a little bit. Let's take 1 minus x squared. Get this. Oh, I mean 2x here. And now the derivative is minus 2x. Like this. So in both cases, the derivative is 0 at the extremum. But in the first case, it goes from negative to positive as x increases. And in the second case, it goes from positive to negative. And that makes sense from the graph of fx. So before the minimum, the graph is decreasing, so negative derivative, and after it's increasing, so positive derivative. And the other way around for the maximum. So we can write out the test. Suppose C is a critical point of continuous function f with f differentiable on, so we use these sorts of sets before, f differentiable on the interval AB with C removed. We write it like this. So I'll draw a picture in a moment. Then moving across C in positive direction, so the first bit, if f prime goes from negative to positive, then f has a local minimum. Let's see. Okay, so let me draw the interval we're using. So it can be red. It's going to be the left-hand point, and then C, and then the right-hand point B. And when I say moving across C in a positive direction, I mean moving like this. So in the examples, C is 0, and as I cross 0, we go from negative to positive, so we have a local minimum, as in the first example. And of course, we have the same thing for a local maximum. If f prime goes, sorry, mistake here, goes from positive to negative, then f has local maximum at C. So that's the example on the right. But there's a third case. And I'll give some examples in a moment. So what if f prime does not change sign? In that case, f has no local extremum. At C. So let's give an example of case 3. If I have fx is x cubed, then f prime x is 3x squared. So the graph looks something like this. But when I do the graph with the derivative, I can see it's always positive. Three x squared. So it's positive on both sides of the critical point. So let's give a proof of one. So this is a good review of what we said last time. So what am I going to do? I'm going to copy what we're trying to prove here. Oh no, I think it's best to do it the other way around. So by assumption, if f prime goes from negative to positive, let's get the picture of the interval. Yeah. So by assumption, f prime goes from negative here to positive here. So f prime is negative on the interval a to c, and f prime is positive on the interval c to b. So by last class, we have that f is decreasing on AC, and it's increasing on CB. And so, if I take x in AC, so f is decreasing on this interval, so the value at x is greater than the value at any larger number, and c is larger. Whereas if I take an x in CB, then the value at x is greater than any smaller number, and c is smaller. So for all x in the big interval a to b, have fx less than or equal to, sorry, I mean greater than or equal to so x equals c is a local minimum. A new page. There's a similar proof for 2. Okay, but now let's give an example of how to use this on a function where we don't know where the minimum is. Because in the example so far, we could just draw the graph and see, but let's do a more complicated function. Let's take fx is cube root of x times x minus 4. So I want to differentiate this to find critical points. So what's the best way to do that? Well, there are different ways. We can use the product rule as it's written, or we can multiply it out like this and differentiate directly. So then we get f prime x is 4 over 3 x to the power 1 over 3. So we reduce that power by 1, the usual rule. And here, I multiply by that 1/3 and I reduce it by 1 to give x to the minus 2 over 3. But this simplifies nicely. 4 over 3 x x minus 1 over x to the power 2 over 3. I'll write it like that. So note that 0 to the power 2 over 3 is 0. So function not defined. Oh, wait, so I have to be careful. Yes. So f prime not defined at 0. But we can try to take the limit. And now the limit as x goes to 0 of 4 over 3 x minus 1, well, that is minus 4 over 3. And the limit as x goes to 0 if the rest, so the 1 over x to the power 2 over 3, well, the bottom goes to 0, so the whole thing has a limit positive infinity. So, in fact, the limit as x goes to 0 of f prime x is minus infinity. And you'll be able to see why this is when I show you the graph. But let's look again for critical points. We can see you put f prime x equals 0, Let's solve this. Let's assume we're not at x equals 0 when the function is not defined. So we solve 4 over 3, x minus 1 equals 0. And that gives me x equals 1. So we have a critical point there. But is it a maximum or a minimum? Well, we can tell just from the function. So x minus 1 changes from negative to positive near x equals 1. And x to the power 2 over 3, well, that equals the cube root of x squared, so it's greater than 0. Always positive. I'm putting these things together, we get that f prime x itself changes from negative to positive near 1. So x equals 1 is a local minimum. And we can see that from the graph. I have the graph somewhere here. No, not that one. I think I have to go back further. I have this one. Yes. I think my iPad has stopped recognizing my finger. It's a problem. There we are. Okay. So this is the graph. And we can see that We have a vertical tangent where the limit of the derivative is minus infinity, and we have here a local minimum. Okay, let's take a break. Okay, starting again, another example. So we've looked at critical points where the derivative is 0, but remember, a critical point can also be where the derivative is not defined. So let's take fx is the square root of the absolute value of x. And then the graph looks like this. So here it has a critical point because the derivative f prime is not defined. So we can see that the function is decreasing up to x equals 0 and then increasing again. And we can check that with the derivative as well. So f prime x, well, let's first do it if x is less than 0. Let's start with the left-hand side. So if x is less than 0, then the absolute value of x is minus x. So we're taking the derivative of this function. And if I was just taking the derivative of the square root of x, I'd have 1 over twice the square root of x. But I have a minus here, so I use the chain rule. So remember, I differentiate what's inside. That just gives me a minus. And then I do the derivative of the outside. So we get that. And that is negative. Whereas if x is positive, then I'm doing the square root of x. So I just get this as the derivative. So here at this same point, I have a local minimum. Okay, so after that, and we'll keep using this technique to find maxima and minima of functions. But a new topic, concavity. So strange word, concavity. So let's draw a picture. It's the best way to explain this. This is the picture. Okay, so I'm going to start a new page. So here's the picture. In this graph, y equals x cubed. On the right, we say it's concave up. And on the left, we say it's concave down. It's because of the way it is curving. So definition, For a differentiable function f, we say firstly, f is concave up on an interval if f prime is increasing on I. And we say it's concave down, like on the left-hand side of the picture. If f prime is decreasing on I. And so, note, concave means this shape, like this. So I used to remember it by thinking of a cave, like a cave in the rock. So to help you remember. Arrow points into cave. And on the left-hand side, that arrow is pointing down. Let me write that here. Here it's pointing down. And on the right-hand side, it's pointing up. Okay. But we measure these things by looking at the derivative. So we have the second derivative test. For this. Say f is differentiable to second order. Means f prime and f double prime both exist. And this is on an interval I. Okay. then if f prime prime is greater than 0 on I, then f is concave up, and if f prime prime is less than 0 on I, then f is concave down. So note, because in these cases, f prime is increasing. So remember from last time, if the derivative is positive, then the function is increasing. So the derivative of f prime is f prime prime, and if that's positive, then the function is increasing. But if it's negative, then f prime is decreasing. So we have these two cases. Okay, so let's do some examples of this. So for example, fx equals x cubed, we have f prime x is 3x squared, and f prime prime is 6x. So that's negative for negative x. So there, f is concave down. So f is concave down for an open interval -∞